Okay, folks, it's good to see you all. I'll go ahead and get started here. Let me go ahead and open this up in prayer, and I'll give a sense of what we're going to be covering today. So, dear Heavenly Father, Lord, I thank you for the chance to be working with each of the students in this course. I pray the material will be clear. Pray that I can communicate with each individual with maybe things that are challenging that they need a little help with. I'm happy to do so. Pray you'd also help them with their spiritual formation, Lord, that they can really get a lot out of what they're doing in terms of the scripture that they're learning in various courses, the things that they're learning and for the theological principles we want to be guiding our lives by, and give them interesting and creative ways for faith integration. In Jesus' name we pray. Amen. Okay, well, today what I wanted to focus on was to spend most of our time going over project 2 and project 3. There are some things I want to introduce and some other things that I want to continue to build on. And so maybe one of the ways to introduce that is just going right to the material. We were just talking about the operating system support and how the system architecture helps out with that. And one of the things that we started to talk about was this table. And there are these various ways that an operating system engages with. And so we have the instruction set, it needs to be engaging with stuff on that. So this defines the machine language instructions that the computer can follow, the boundary between the hardware and the software. And then we have this interesting thing, the application binary interface, and it defines a standard for binary portability across programs. And so executables 1 to 2, it can load those and run them. And so it defines the system call interface to the operating system, the hardware resources and services through available in a system through the user ISA, the instruction set architecture. So these things could be actually written in C++, or they could be written in assembler. And I'm going to be referring to that a little bit when I start talking about stuff in an assembly language in just a minute. And then the other one that we mentioned, the application programming interface. This gives a program access to the hardware resources and services available in system through the user ISA, implemented with high-level language HLL library calls. And then using the API enables application software to be ported easily to other systems that support the same API. So just as long as things were compiled for the same CPU and you're still using the same interfaces, there is a fair amount of portability that can actually take place. And there actually is some interesting blurring of capability. A lot of things that were done on the desktop were with the x86 architecture, and now we're seeing with both Apple and Windows going into convergence, where there's now not only supporting what's going on with Windows with an x86 architecture, but now going to an ARM Windows environment. And now you have Mac OS as both for Apple Silicon, which is ARM based, or the Intel architecture. So that's kind of an introductory comment I wanted to give you. And then I'm going to just show a couple of references to this kind of information. I have something from both Microsoft and Apple. And so if you look at the Apple's Windows app development, this is what I found here. And so I did a search looking for Windows ARM and looking at the development that's there. And a lot of it is done in C++, but you see that now we're building for, say we're having applications we want it to work in an x86 architecture as well as an ARM architecture. There's things that need to be thought through. And so this is where it highlights what they're using. They're using the ARM 64, so 64-bit ARM architecture. And you can actually utilize assembly language things that are compiled and executed. And so this is just a document that walks through some of that. And so maybe this kind of way of looking at it, this is going to be an example of what we're doing in assembly language programming. And I'm trying to give a couple examples. We're using the MIPS emulator. And there's also another one I just introduced that I'm still checking out, but I'll continue to give some thoughts on that. So this document talks about writing in assembly language. It also talks a little bit about comparing that with what it would be in C++. C++, you can actually get access. In some ways, it can give you a look and feel for some aspects of assembly language. It's not going to be quite as efficient, but there is some things like that are available. And so I'm not going to get into this article in detail. This is more assembly language here. This is some stuff that we have. So first of all, just wanted to give a perspective on what Windows is doing with ARM architecture. If I was to look in not the ARM portion, but the Windows x86 portion, I would see the same thing, but it would be a slightly different assembly language. It would be one for the Intel-based architecture. Then now with what's going on with Apple, they've gone full bore. All of their processors, both, I mean, I shouldn't say both, but all their laptops, their tablets, and their phones are all using this Apple Silicon. And so this is just part of what's the Xcode. And for some that maybe you haven't heard of this is the development tools that Apple makes for developers. And so buried into what is here is this section when it talks about the Apple Silicon and what you need to be doing for that. And so you can write code, ARM64 code for the Apple platforms. And so there are a few nuances that they mentioned that the Apple Silicon varies a little bit from the standards. And so they give some perspective on that in here. So that's really what I just wanted to mention at the moment, was just talk about sort of an existence proof of what's available both for Apple and Microsoft, things that they're doing for the ARM architecture and using that in their computing environments. So with that as a maybe an introduction, let me just spend a little bit of time talking about a couple of things related to assembly language. And so this would be the first of a couple more focused set of charts that I'll be sharing in our class here. So I put this together a couple years ago and was trying to be comparing between the ARMs or MIPS and the x86 architecture. And so this is just a synopsis of that. And so the x86 architecture, originally it was in 32-bit and there was a big jump. Some of you may have some memory of what that was like, that there were times that was sort of distraddling and was having both, and now we're full bore into 64-bit. The next C chain will be going to 128 bits, and I've started to hear some things on that regard. And so now, interesting enough, in the last handful of years, there's been a lot of insurgence with the ARM of becoming not only for embedded systems, but actually for other platforms as well. So the iPhone, the iPad, now all of the Apple, and Microsoft is including it within its various types of offerings. And so there was also something historically with the Mac that they had the PowerPC. This was an IBM-based processor. And so that is something that is out there. And ARM now is ARM64, and there's a couple other nuances. We'll get into that a little bit later in the course, but those are just a few things to be thinking about. So we have been going back and forth between the Intel architecture and the ARM architecture. I'm not going to go over this chart, but this was just a few years ago, giving a sense of what one of the Intel processors, the Itanium, that they were leveraging. So the x86 assembly language command sets is actually different than what we see in the ARM. They actually have a lot of different commands. And so this was just something just more, probably more for just shock and awe. There's like over just about 1,000 different commands. And so there's a lot more nuances of things that are out there. And so this is just gives you an idea that maybe it's better if we're going to have a brief survey of what it's like to be an assembly language, go into something that's not quite as exhaustive in terms of the commands. Well, if I was to do this Hello World program that I've shown you in class, and I'll talk about it a little bit more today, this is how it would be done with an x86 assembly language. And if you were to just to roughly look at this, you would see that there is some similarities. Instead of a system call, they call it a call to kernel. And so basically you load information here, or you have the dot data. That's something that we've seen with what we have here. And so we have ASCII codes here, a hello world. And that's what we have here. And then we see that these are called one at a time. This gives it the length. Then we have the actual message. We put them into the right registers. Then we do the system call for a system write. And then the last thing we do, we set things up to do a clean exit as we had with the ARM architecture. So that's maybe just a little bit of a reminder. So this is what it would be. This is, you can kind of scroll back and forth, the Intel version of this program versus the ARM's, the approach to this. And I'll have this open in a second in the Mars emulator that we have been using, but just as a reminder. So the way that it's architected with this version is a syscall 4 is to print, a syscall 10 is for an exit. Here we have the message formatted for hello world. The \n just does a carriage return. And so that's a non-printable character, but it gives you more information of how you're going to engage with the terminal, your console. And so those are things that we have there. So maybe that's just a first perspective. So we're not actually, at least at this moment, the way I have architected the course, we're not doing assembly language programming in Intel, but we're doing things with the ARM assembly language. One of the things that I did get for some feedback on the course, they were wondering why we're maybe using this emulator, number one, and it is getting kind of old. And so they're looking for other things that I would like to, maybe I could use that might be a little bit better. And so maybe I just do this as a quick survey question if people would like to share. If we did not do programming in assembly language, would you want to do C++, or what is your impression about what we're doing in C++ in assembly language programming? Anybody have a thought on that? Anybody familiar with an emulator that you've been exposed to that you like?
What's the difference between this and a C++ as far as like, does one function faster than the other, or is it just completely different software?
Assembly language will actually execute things faster. So if speed and low resources overhead are the priority, then doing things in assembly is the best way to do it. C++ can, in some instances, get close to that kind of performance, but that's not always the case. And so say you're trying to do your power constraints, say on a cell phone, that would be an example where there could be situations where you have to be really efficient. And so diving down into doing assembly language programming, at least for some key portions, might be something that you would want to do. Anybody else have any impressions about what we're doing with assembly language? Any emulators you've been exposed to? Okay, well, thank you, Austin. So Austin said that he just did a assembly language class where they did everything in VS Code. And so that's a possible platform that I could consider, that if anybody does have impressions, that would be fine. Well, let me give another thing that I wanted to get some class participation. And if some would like to talk directly, that would be great. If you just want to send it in the chat, just let me know that way. What do you want to accomplish with your assembly language project? Let's just have a little bit of discussion. If you've actually thought that through, what exactly do you want to code? That will help me in terms of what I would be sharing the next handful of Thursdays for our lab time. Anybody have something they'd like to mention?
For my project, I would like to do an assembly code where the test buttons that I showed on the digital logic actually works, where it says test button started, 50% done, and then 100% complete, something along those lines.
Okay, well, let's unpack that a little bit, David, and we've had a little bit of discussion on that. Maybe I'll just do a precursor. There's been a handful of people that I've been able to help them get their Arduino projects going. And so first of all, David, we were able to troubleshoot that the install wasn't working quite right. So we uninstalled, did a reboot, did a clean reboot, install, and then things got working. Another example of that, Isabel, I was able to work with her. For some of you, it may be kind of scary to pull out this Arduino kit and actually plug something into your computer. And so it actually can be a lot of fun once you get past that initial apprehension of what might happen. And so I was grateful for that. And then last Thursday, I was able to help Josiah get his configuration up and running. It turns out that what he conveyed was, it was when he chose something different than the Arduino Uno, that was what was preventing it from getting the communication that was trying to have people get a chance to see that on last Thursday. So let's look at what David had mentioned for his project. And so I'll let David communicate on this, but others as well. How do you think, if you were trying to make things simple and accessible, that you might try and do the kind of capability so there aren't any push buttons in assembly language? So how would we be modeling different levels of performance that we're trying to go from, say, a digital circuit that we program now, trying to think about doing some of that in assembly language? So maybe if you want to start the conversation on that thread, David, feel free.
Probably like possibly making like an app. I know it's kind of like extensive, but for a push button to work, you could probably have it like on switching it to a different setting, it so that the circuit knows that it's going from a default setting to a specific setting that you're looking for, like testing and actually wanting to complete something versus what's already defaulted to.
Yeah, what I would have you think about, David, is so a switch could be you actually request an input from the console. Is it on or off? And so that might be the way that you would be representing a switch. And then you write that to a register. And then you do like a logical operation where you compare two registers, do a logic and operation, and try that. Those are the kind of things that I would have you think about of how you're going to be simplifying it. And so it's especially for some, maybe most of you, you've never done assembly language, try and make it as simple as possible to see how you could actually do something like that. And so that's what I would have you think about, David. Does that make sense?
Yes, thank you.
Let me get just around the virtual room. Anybody else? Does that make sense? You can do a thumbs up if you like, but just give me some feedback. I'm trying to make what we're doing here useful. And one of the reasons why I'm trying to have it be a lab time, that I would hope that you have these tools we're using open. Try some of this as I'm showing you stuff, and let's go ahead and take advantage of that time and make it productive. And so if you do have any questions, let's work that through. Okay, I'm still sharing my screen, and so let me show you what I've got here for another sample assembly program. And this is, there's a couple things that you're seeing, at least what we're using for the Mars emulator. You declare main as a global function. So this is what we have here. All the program code is placed after the .text assembler directive. And so this is where we have that. So here, this represents the mounting point. And so this is where the emulator and what's going on in the computer, it has to start to be assigning registers, memory, based on what you are doing. So here this is LI, stands for load immediate. And you can see how I've mentioned this before in assembly language. It's common that you have a lot more comments than you actually have lines of code. And so this is what we have. So this LI is a load immediate. So you're loading 25 into the register T2. So this is over here. Then you're loading the word stored in value. And the value here is, there's a word and it's 12. We're putting value into T3. And so I haven't run this program yet, so we'll see that in a little bit. And then we do an add. So we can be adding 25 and 12. We can do a subtract. And so those are things that we have. And then we store the answer in Z. And so that's what we have there for that beginning. So then we want to do an exit the program by means of the syscall. And so the exit is syscall 10. There are many syscalls, so we want to be picking the one we know that it's 10 is where we want to be doing for this. By placing its code in register V0, the code X for exit is 10. We do that, so we set this into the register, then we do a syscall, and then we've completed it. So we have this .global, we have this .text, and .data for these directives that we see here. So let me go ahead and assemble that. And we can just go through this one step at a time to see how this would actually work out. So here we have the load immediate value into T2. So now we have 25 in register T2. Do the next single step. This puts the value that we've defined, which, as we might remember here, is 12, into register T3. So let's go in and execute that and see. This is another thing that the assembler actually divided this into two commands. So it broke down what we had here and made it into two commands. So it executed the first one, then executing the second one, puts 12 in register T3. We have that. The next thing we want to do is add them. And so it's actually going to add them and put it into T4. So T4, 25 plus 12 is 37. We see that, and then we're going to subtract them, and it's going to be putting that into T5. So we have those. So we've used T2, T3, T4, and T5. All of that is there. Then we do a store of the results. This is actually broken into 2 commands. And then we want to do a clean exit. And so we put things into the right location to exit cleanly. Do the exit, and then the program is terminated. So that just gives you another example of a program. I showed you several times already the hello world, and this is just literally communicating with the console, printing something out. Now we could get a chance to be engaging and manipulating things. And so, like what you mentioned, David, even for a first, before you actually try and read from the command line, you could just hard code it. And so here you have add, but you can do like an and. So let's just go to the list of commands. So if we wanted to be doing a logical and, I like the way that they lay this out, because all the commands are put in an easily accessible way of seeing it. Well, they have the XOR down here, bitwise exclusive OR. Maybe you might remember that term for, it's a variant of the OR. If somebody finds it before me, let me know. Here is the OR, here is the NOR. So we have those. Maybe it's all the way. Yeah, here it is. Here's a logical and. Okay, so maybe David, you might want to try that. So instead of having this add, you could just change this to and. Maybe if you wanted to, just as you're trying things, you could set, do the other one for or. And so the syntax is pretty straightforward. You just have to be, one of the things you have to be mindful of is you're comparing things, and then you're putting into another register, and this will help you get a chance to understand which registers are the inputs and what register is the output. Okay, so let me do a little bit of check for feedback. Thumbs up, did people follow that? If not, thumbs down. Give me some, anybody have any questions on that? Okay. So that's what I wanted to show you for this. The other thing that I introduced last Thursday, and so this is another emulator that I'm still evaluating, so I don't have this all cleanly figured out. But one of the things that I did, this is one of the programs that they have embedded in here. If you go to the help manual, and then at the very end, there's code examples. And this is the way that we have here. And so I was starting to modify this a little bit. So this is what I have because you can see I've actually was running this a little bit earlier to try, and right now the version isn't 0.5, it's is what they originally had. And so this was the way it came out, and it had it as a 5th of June. Well, it's actually a version 1.2 now. And so this is the things that I started to manipulate. And so you can see this is kind of like the Hello World program, but it's a little bit more complicated. The syscalls are a little bit different. The terminate is a syscall 0. The print is a syscall 5 versus syscall 4. And so these are just some of the characteristics of this emulator that I'm still running to ground. So this is a way that you can have a formatted way of putting something out to the console that's a little bit more complicated. And so this is saying the something of a month. And so these are the things that will be the order of these things make a difference. So what it's going to be printing out is edu MIP64 version something is being tested, and then it gives a date. And so that's what shows up here. And so they hard coded it for the 5th of July. I just manipulated it a little bit here. And so I changed it to the 9th of July. I left it June. My wife's name is June, so I tend to like that month. So, and then it had like a major version and a minor version. So instead of having it be 0.5, I changed it to 1.2, and that's what I had figured out. What I've also started to do is I've started to put in more comments here to give me a brain jog on this. The way that this this development environment, it doesn't actually have this kind of a window that's built in like the Mars program. And so that's one of the reasons why I'm opening up another editor. And that's kind of the setup for what you're doing. And then you actually get into the code. And so you have the dot data, the dot code. And I'll open up the manual. Now look at the instruction set. It's a little bit more difficult to find the instructions. Let me get my window back over here. So if I wanted to be looking up this d-add immediate, d-add I. Well, here, this is sums the contents of the 64 registers, R, S, and RT, and then puts the result in RD. So this isn't quite the one that we're doing, but this is some of the nuances that you have, variations of these basic commands. And I think I found the d-add I someplace here. Yeah, here it is. So this is immediate. And so basically what immediate means, like when we saw with the first moving things into registers and out of registers, immediate is we have a value that's here. And so it's not adding to registers, it's adding a value that you supply at the terminal. And so this formatted string is going to be added to R0, and it's going to be put out into R5. So what this is trying to show you, instead of just printing out hello world, we can actually customize a string. So this is something that if you were to do in Python or Java or C++, it just gives you an idea. There's a more complicated construct that they're trying to give you an example of how that can be done. So that's the first command that we have. I'll just do one more command and then I'll do a check and see if people want me to go through this line by line. So like I said, it's a little bit harder to find the various commands here. Um, Well, I'm not going to take too much time trying to track that down. I'll look it up and give it, and we can continue that. But let me get a thumbs up here. Is everybody following what I'm doing here? I know this is a different tool that we're using. I'll
Yes.
go ahead and execute this program. It's already loaded. And so let me move this over someplace else. And we really haven't gotten into some of these things, so I'm not introducing some of the things where there's some acronyms that are being used here. And this picture down here will become more useful. This is one of the things that I like about this emulator. So I'll just go ahead and I'll load this program to start from scratch. And then I'll do a single step. Hard to not have things in the way. And so these are the lines of code. It doesn't have any of the comments that I had. And so, and this starts to show you the pipeline. And so we have this first command is now moved to this next state. And so this is one of the things that gives you an idea of what's going on with things here. And we'll be talking a little bit of happens as like here, there wasn't a new instruction that was added. And so it takes actually two clock cycles for it to execute. Actually more than that, there's several. So then we go on to the next level as commands are propagating through this pipeline that we have, this computing pipeline. So just go ahead and go through this. So you can see that at any one time, there's like the capacity for about 4 commands to be operating. And then at the very end, we'll start to slim down. 4 or 5 are actually processing. And then we slowly wind down until we get to finishing the very last command. And the last thing it does, it prints out the result at the console. So that just gives you another run through of another way of looking at what it's like to be having a pipeline architecture and what we have from that point of view. Any comments or questions on what I've shared on that? Okay, well, let me now move over to project 3 a little bit. And I just have a handful of charts that I'll share about what is this Arduino. I'll mention a term called a microcontroller. This is an example of a more focused. A microcontroller is like, it's not quite a CPU, but it has some more focused capabilities. So this is moving in the direction of an embedded system. And some of you may take Dr. Ye's course, Internet of Things, and you'll get a chance to be playing with a more reduced type of Arduino so this might be helpful for that in terms of thinking about that larger context. So this is just a summary that we're getting familiar with computer architecture and organization, just some terms. Now that you're seeing that we have computer organization, we have started to talk about the implementation. And so these are all things that we're getting exposed to. You've heard me talk a lot about the Harvard, the von Neumann architecture. There's also a variant of that called the Harvard architecture, where it actually has two specific areas of the memory that don't overlap, and so that's a possibility. So Arduino is an open source electronics platform. So the hardware and the software is all open source. So it has kind of an interesting way of doing things. And so we can do a lot of things. You can turn on or off an LED. You can have a light go on if a sensor detects something. You can actually have push buttons. And so the sky's the limit with what you can do, but we're trying to give some basic introduction with what we're doing in this course. And so you have the computer with your USB connection plugs into the Arduino, and then you have a logic board that you put specific things that this is where you're engaging with the physical world. And so this is where I start talking about cyber physical. This is your physical, and your cyber, your computer, and what you're doing with the hardware is all in this other end. Interesting, if you have this, if you put in a battery with the Arduino, once you've uploaded the program, you can actually take away this other stuff. What we're going to be doing for the class as a default is you're actually getting power as well as programming to the Arduino through your USB. And that's also responding back. I've shown you like the plotting function and things like that you can see coming out from the Arduino kit. So the Arduino Uno is really a workhorse for the family of Arduino types of microcontrollers that you can be using. And so I try to steer people in the direction of having that. And I think most of you, maybe Josiah is an example of someone has a slightly different one. And so I'll have a couple of slides that I'll just talk about the different elements that are there. And actually there's two microcontrollers on it. And so I had mentioned a term that I started to coin is like you have the main CPU, and then you have like first lieutenants that actually are subservient to this higher level function. And so this is the first of two pictures that I'll have a chance to be showing you. You have where you plug in with your USB. It also supplies power, 5 volts. You can actually have an external power supply, and so you can either have batteries or you can have external power. And so this could be running on its own without anything else. What you're going to see is there's pins on the top and the bottom. These are the things that you're going to be plugging into your wiring board. And we'll get into that in a little bit more. But what I wanted to introduce for this part of the discussion is to be focusing on these microcontrollers and get a little bit more specifics about that. So the main microcontroller is here. This is the one that connects the information that's going in and out of these pins. And so if it begins with an A, it means it's an analog. If it here it has the digital, and so there's a variety. There's more of those. You can actually have ground and various types of power. So you can actually be powering your wiring board with your Arduino kit. And so this is why it's going to be important to at least have ground, and most likely you'll be using 5 volts for that. And so there's still some things that are over the different components, but I'm just trying to give you a little bit more insight of what's going on in the innards of the microcontroller here. This is a schematic. This is an example of why an Arduino Uno is open source, because they publish and you can download this. And so with this, you could create your own version of an Arduino. And so the things that you got off Amazon, I think probably most everybody did that. It may not actually be made by Arduino, it may be some other manufacturer. And so I'm not going to get into the details of the schematic, but here is the main microcontroller. This is the one that communicates with these pins, all of these pins here. So this is the main microcontroller. And then you have another one. This is dedicated for communicating with the USB. So it takes the information from the USB, translates it, and routes it to the right place. And so this is focused on I/O. And this is the central thing where the main logic that you're trying to program is done with this microcontroller. So that's one of the insights that I just wanted to highlight for here. So microcontroller is a computer present in a single integrated circuit, which is dedicated to perform one task and execute one specific application. Like a garage door opener or automatic door opener if you go to the store. Those are the things that it has. And so it contains memory, programmable input and output peripherals and processors. So it has the basic elements of a Von Neumann architecture, which we've already been introduced. So it's mostly designed for the embedded applications. And so at a very rough sense, you could pretend like we're trying to program a capability, whatever it is, for a cell phone, a camera, but it also could be Internet of Things, thinking of a microwave, or washing machines. It's getting to be more and more common that you can actually directly, say from your cell phone, access your oven, your garage door, your washing machine, turn it on or off, get diagnostic information, and the sky is the limit. So these are some detailed charts. I won't go over them except to give a little bit of a perspective on them. So we have the main Arduino chip. And so this is the capability that is on it. So it's like a Swiss Army knife. It can do all kinds of things. And so when you're doing one specific project, it means that some of the other capability that is available won't be used, but that's perfectly fine. But this just gives you a wide perspective of the various things that it has. So it has memory, both flash, and so you upload your program to the Arduino, and it maintains that memory. Like what I have shown one or two examples in class for kits I've already put together. Literally, I plug it into the computer, but it just to give its power, and it actually runs, and I can actually have it communicate directly to my computer as it has this relay of information through this this first lieutenant microcontroller that's sharing that information back and forth with the USB. So this is some of the details. It has this analog to digital converter. So it does things in the analog world, but it has to take that information in. And the first thing it hits is an analog to digital converter. It digitizes that information. That's all there. So this is just a couple of things that I'm pointing out that are available. Programmable I/O lines. We're going to be using that. This is how we're going to be plugging into LEDs, switches, whatever that you guys think that you would like. And this is now digging deep into what's going on in the chip. And so like I'm looking now inside of here, giving a very quick perspective on that. And so it has a CPU. It has its flash memory and SRAM. These are terms that we've already have introduced. And it has the essence of what is it's like the heart of what's going on in this Arduino. And then we just have to have the wiring so it's more convenient for us to get access to this information. And that's why we have this all lined up on the edges for inputs and outputs on different sides of the board. So that's a synopsis of that, just a blow up of the pinouts. If I was to actually have a schematic, like this. This is shown a slightly different way because it doesn't necessarily have to have all of the pins on the orientation where the actual chip is, but this is more just to give it a conceptually a way to show you what's connected to what. So it's a slight difference from this, but this now just gives you what it would look like if you're trying to figure out where you're going to put this on your board, and then you want to figure out what's going to go to what pin. Those are the things that you have there. Then you have this first lieutenant one. This is the one that deals with the USB connection. That's the input and output. And so that is its main function, that you have a processing capability that deals directly with I/O. And that's something that we covered in class already to get some exposure to what that's like. So it's a USB 2.0. So for what we're doing, that's adequate. I'm sure that in future generations, it'll be 3.0, 3.1, USB-C, all of those things will be things that are coming forward. So it once again, it's a Swiss Army knife, and there's lots of capability that are available, only a portion of what we're using for this. This gives you an idea of its pinout, and it's slightly different. It's not just having things on 2 sides, but it actually has on 4 sides. So it's actually a small chip, but there's a big requirement for input and output. And so that's the reason why they have it on all 4 sides. You can see how it has like this little cutout here. This is one of the things that helps to make it straightforward when you actually put this into a socket, that you put it in the right orientation. So those are a couple little things that I could be mentioning. I'll skip over these. And since we have been talking about assembly language, you can actually have assembly language loaded into an Arduino. We're not going to do this, but this is more just trying to give an idea of an existence proof, that stuff that's out there. So that's really what I wanted to cover. You all should have had CS160 or equivalent. These are just some charts. I taught this course a couple years ago. And these are just direct screen captures from some of the tables that were where the digital logic was introduced, but from the point of view of what you had from CS160. So that's what I wanted to cover on that. So let me see if there's any comments or questions there.